Hello, this is topic 7.2. We're going to be looking at how to draw what's called Lewis structures with single bonds. The only resource, well, let's backtrack. Two resources you're going to need is your periodic table and your polyatomic list. So we've talked about chemical naming now, and we've also talked about the idea that elements can either transfer or share electrons in a way to get to 8 valence electrons. And so that's kind of like the Goldilocks and the Three Bears rule, that typically all atoms, there's a few exceptions to the rules, and we'll talk about those here momentarily, they want 8 valence electrons to give them the octet. Again, that goes all the way back to electron configurations with the idea that they want to fill that 2s2 and 2p6 to get to that 8 electron rule. And so what we can do is start to look at how are those electrons distributed amongst the atoms, and then that can start to describe some of the properties and behaviors because it determines the shape of these things. So we're going to eventually get to the point that we look at these three-dimensionally in terms of what do they represent. So the front side of your map, or the front side of your notes, is like a map, I should say. And so I like to say that there's a method to my madness, and that there's a reason why I set things up the way that I do. And so this front side of your notes, when we draw a Lewis structure, there's a lot that goes on a problem that it's hard to go back and look at and remember what we did first and what we did second. So the idea here is this is going to kind of be like a sketch where it shows you the procedural steps of what to do. So if you get stuck on a problem, go back to this front side of the notes, and that gives you a direction on what to do. So the first thing that you need in order to correctly draw a Lewis structure is you need a chemical formula. So the sample we're going to work on this front side is for the compound carbon tetrafluoride. So the formula is using prefixes. So we have CF4 because carbon has no prefix, and tetra means 4. So that's going to be the example that's going to be used on this whole front side. So from there, what we need to know about our molecule here is how many valence electrons are available. So looking at my periodic table, if you remember, carbon is in family 14. If you cover up the 1, that means it has 4 valence electrons. Fluorine is a halogen. It's in family 17. Therefore, it has 7 valence electrons. And so when we go to write this out, we kind of do a just small calculation here in that we have carbon and fluorine. And so carbon, we have 1 of them in our chemical formula, and fluorine, we have 4. So again, I just got that information from my subscripts here. So what we're doing now is we said carbon has 4 valence electrons and fluorine has 7. So 7 times 4 is 28, plus 4 gives us that there are 32 total valence electrons available within this molecule. The next thing we can do is calculate the number of bond pairs. And so when electrons are shared in a molecule, they always are shared in a pair, where one is sharing its valence electron with another electron from the other element and vice versa. And so when we go to look at how many bond pairs or how many pairs of electrons we have, we just take that pool of electrons, divide it in half, and there are 16 total BP or bond pairs available in this molecule. So the next thing, and this is just kind of like chemical naming. The more you do it, it's kind of like riding a bike and you get better at it. So we have lots of examples we'll work through. And so I'll kind of work through these rules here as we get to that point. And so what we're going to do here is start to look at a two-dimensional structure for what does this molecule actually look like. If we could zoom in, if I had a Miss Frizzle magic school bus and we could zoom in, what does this look like? And so when we zoom in, if carbon is present, that will be your central atom. And so we do have carbon. So carbon is going to be the center. And so that means these 4 fluorines are going to surround the carbon. Okay, so it's kind of like carbon is like the sun and the fluorine are kind of like planets, so to speak, as a way to kind of give you an analogy. All right, so from there, we have to represent that electrons are being shared. So we're going to take this drawing from up above, but we're going to change it in this step. And so what we're going to add is a dash. And that dash represents a bonded pair of electrons, and a bond is always consistent of 2 electrons. So we have to show that there's sharing of electrons taking place between the carbon and the fluorine atoms. That's taking place between all the carbons and the fluorines. And so the idea here is that we're saying that this carbon and this fluorine are sharing 2 electrons here. But not only is carbon doing that with 1 fluorine, it's doing that with 4 fluorine. So right now, surrounding that central atom, the carbon, we have 2, 4, 6, 8 electrons. And so going back to that analogy of Goldilocks and the 3 bears, carbon is just right. It has completed its octet by sharing one of its electrons with fluorine, and fluorine vice versa, sharing in return. And that is how it was able to complete that octet, by making that bond. And so what we have to now take care of, so again, the next step is that carbon has its octet, but our outlying fluorines do not. So what I said at the beginning, we calculated that there's 32 valence electrons available. Right now, again, we've used 2, 4, 6, 8. So again, we now have 24 remaining electrons that must be spent. This is kind of like an electron allowance, and all the electrons must be spent. So we're going to add something new to our diagram called lone pairs. So the lone pairs are shown as a set of dots. Again, that's what it means, is a lone pair. And again, those are 2 electrons. So fluorine doesn't have to share all electrons with carbon in order to complete their octets. And so they can do that by having electrons all to themselves. Those are called lone pairs. So this fluorine has 2 electrons. That means fluorine needs a grand total of 8. Well, 8 minus 2 means fluorine needs 6 more electrons to be happy. So I'm going to place 1, 2, 3 sets of lone pairs around this fluorine. That gives me 2, 4, 6, 8 electrons. Fluorine is now a happy, complete atom with its octet. What I do the 1 fluorine, all the other fluorines need as well. And so the last thing that happens, we now have, this is a Lewis structure. So when you get to your homework, this is basically your final answer. And you're not going to do those 5 previous steps. It's all going to happen simultaneously within the same diagram. What this does is it shows you a procedural step of what to do. So the last thing you always want to do is a couple of things. You want to make sure that you have a complete octet on all of your atoms. We did that with the carbon with the 2, 4, 6, 8. We have 2, 4, 6, 8. What we did to 1 fluorine, we did to the others, so that's good. The last thing you want to always check is, did you spend all of your electrons? So here you're going to be counting by 2 champions, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So all 32 electrons are used. Everybody has an octet. We are now done, and this is your final answer. Okay? So if you look at the second page of the notes, we're going to do the same thing, but we're not going to do it as this big drawn out process. We're going to have one Lewis structure done all at once. We're not going to show all the steps. So if you look at the front side or the very first page, the first step was we need a formula. We have nitrogen trifluoride. So we can see prefixes because a lot of these are molecules, meaning they're covalent bonds made up of nonmetals. So our formula is NF3. Our next step was to get a valence electron total. So we have nitrogen, and there's 1 of them. Fluorine, there's 3 of them. You then go to your periodic table. Nitrogen's in family 15, therefore it has 5 electrons. Fluorine is still in family 17, so it still has 7. So we multiply this by 5, we multiply this by 7, add them up, and we get 26 electrons. Okay, so the next thing is we are now ready to start drawing our Lewis structure. In the previous example, we said carbon was the central atom. In this scenario, it's going to usually be odd man in the middle, whatever you have 1 of, which in this case, it's nitrogen. So nitrogen's our central atom, and our diagram should include 3 fluorines. So I'm going to go ahead and put in my bonds and go ahead and add my 3 fluorines. The next step that we did on the front side was we completed the octet on our central atom, which happened by completing and adding all 4 fluorines. What we have right now is only 2, for 6 electrons on our central atom. We need to complete its octet. Therefore, we're going to add a lone pair. That gets us to 8 electrons on the nitrogen atom. It now has its complete octet. I now need to work on completing the octet for my remaining atoms, the fluorine. Again, that dash is a single bond, therefore fluorine has 2 electrons. It is like nitrogen in that it also wants an octet, so we're going to go ahead and add our lone pairs, and it needs 6 to get to 8. Like I said, and this will be important for our next topic, is you always want to make sure that you don't overspend your electrons and that you've completed the octet. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So we spent our electrons, so we're good there. Nitrogen has its octet. All the fluorines are the same with a single bond and 3 lone pairs. That gives us 8 electrons. We now are done. Our next example is nitrogen trihydride, and we're going to see a change in what's going to go on in this particular example. Prefixes are telling me that we have 1 nitrogen and 3 hydrogens. Nitrogen we just used, we have 1 of them. It has 5 valence electrons. Hydrogen we have 3 of them. It's in family 1, therefore it has 1 valence electron. So this one only has 8 electrons to spend. However, like the last example, odd man in the middle, so we're going to go ahead and place nitrogen as my central atom. Go ahead and attach my 3 hydrogen. And like the last example, we've used 2, 4, 6 electrons, so I'm going to place a lone pair on this nitrogen here. If you look, that's 8 electrons in our diagram, and we've spent them all. So you're probably thinking, how am I going to complete the octet on hydrogen? Hydrogen is one of the few elements, usually it's atomic number 1 through 5. Those are content with having just 2 valence electrons. And so if you go back to electron configurations, it goes back to that 1s2 and wanting to fill that. So again, hydrogen there is content with 2 electrons. So you will only see hydrogen with a single bond. You will never see hydrogen with lone pairs around it. Okay, so that one is done. We have dihydrogen monoxide. So we have dihydrogen, so H2, monoxide meaning, so water. Hydrogen, we have 2 of them with 1 valence electron. Oxygen, there's 1. It's in family 16, so it has 6 valence electrons. So like the last diagram, we have 8 electrons. We pick our central atom. Odd man in the middle is going to be the oxygen. And then we have 2 hydrogen. So somewhere off our hydrogen, we're going to place, or off the oxygen, we're going to place 2 hydrogen. Again, hydrogen's already happy. As soon as you've bonded it, you no longer need to worry about completing anything else with hydrogen because, again, it wants a duet or 2 electrons. So our central atom, though, is unhappy. It has 2, 4 electrons. We've spent 4. We have 4 remaining. That means I can go ahead and add 2 lone pairs to this oxygen. That then spends all 8 electrons, completes the octet, and I now have a complete Lewis structure. So the ammonium ion, so this is where you need your polyatomic lists. So ammonium, if you look it up, is NH4, and it has a +1 charge, and that is important. That's why I threw this example in here. So nitrogen, there's 1. It has 5 valence electrons. Hydrogen, there's 4 of them. It has 1 valence electron. That gives us 9 electrons. You will never have an odd number of electrons to spend. If you do, that gets into a whole nother thing of radicals, not like radicals in math. If you go on to take AP chemistry, they may spend some time with that in that course. So the thing that we have to then account for is that it has a +1 charge. You are not going to add 1 electron. A positive charge means a loss of electrons has taken place. Therefore, you're going to subtract. We have 8 electrons. Okay. So again, if you're working with an ion and it has a charge, make sure you account for that. Odd man in the middle, that's going to give us nitrogen as our central atom. We have 4 hydrogens. In adding those 4 hydrogens, we've added 4 bonds or 8 electrons, so the nitrogen's happy, hydrogen's good with the bond, and that example is done. So I have one last example that I really want to tackle with you, and that's dihydrogen tetrahydride. So that means H2. Oh, that's what I realize now. This one had a typo. This should be dinitrogen. I thought that was kind of weird to have hydrogen, hydrogen. So anyways, going back and looking over my typo, it's really dinitrogen tetrahydride. And so we have N2H4 as our formula. So nitrogen, we have 2 of them. Hydrogen, we have 4. Nitrogen has 5 valence electrons. Hydrogen has 1. So we have 14 electrons to spend. The reason why I want to look at this one last example is in this scenario, we do not have a true central atom like we did in the previous examples. So what needs to take place here is that you make something symmetrical. And so you start with kind of your odd man, so to speak, but your backbone, or what you're going to start with, is these 2 nitrogens. So start with the 2 nitrogens in the center. They're going to then split up the hydrogens. So there's 4 of them to split. That means each nitrogen will receive 2. Okay, so double checking a couple of things. Each part is symmetrical, so I'm going to kind of cover this part up for now. And we have 2, 4, 6 electrons bonded to that nitrogen. Therefore, it needs 2 more to be content. Nitrogen here on the right is 2, 4, 6 as well. And so this also is going to need a lone pair. So the last thing you want to always double check is make sure that we did not overspend our 14 electrons. So we have 2, 4, 6, 8, 10, 12, 14. All 14 electrons are used, all the octets are complete, and we now have a Lewis structure. If you have any questions or need any extra help, please reach out to me.